Hello everyone. So today's topic is about for identifying and mitigating vulnerabilities in FSM. First of all, let's see what is FSM. FSM is a controller which will get input. Depending on the input, it's going to change from one state to another. Here we are taking a very easy example where you can see depending on the enable signal, it will go from one state to another. So a basic FSM is this one. Let's go further. For this FSM, we wrote a simplest Verilog code where you can understand they have 4 state. So we need 2 register in order to bring up this 4 state. And this is the sample Verilog code. And here you can see for this for this 2 register, you will have 4 state or 4 combinations. All these 4 combination will be used while synthesizing. Let's take what will happen if you have 5 state. Here we took a AES encryption FSM. So in this FSM we have 5 state. In this 5 state, when if I want to use, I need at least 3 register. But this 3 register will give you 8 combinations. Out of this 8 combinations, you will use only first 5 combination because you have only 5 states. So what will happen to this remaining 3 state after synthesis? These 3 state will become into don't care state, and these don't care state can access any state whichever it's there. So it can access some state, it can go to final round or initial round, or it can just be idle. So vulnerabilities. Why FSM is vulnerable? Because here in this example we saw there is 3 don't care state. These 3 don't care state can be used by the attackers to inject fault. So as I told you before, that is fault can be easily injected. For that purpose, we need AVFSM technique in order to mitigate that. Let's see about this. Here in this paper, they gave a quantitatively analysis and evaluates acceptability of an FSM against fault injection and Trojan attack. And prior to this, there has been many techniques which has been told for FSM, but nothing took consideration of this synthesis tools, including this don't care states. So this is a first systematic approach where we are using these techniques. And basically in this threat model, you can see, as I discussed before, there are 5 states. These 3 states will be don't care state. This can even directly access the final round. So this final round is the protected state, and this is the authorized state do round. So to this final round, generally you will be having only one state which will access. Other states cannot access that. But because it has don't care state, it can easily bypass that and it can access the final round. So there are 2 things which mainly can include the fault injection. One is fault injection attack and another is Trojan attack. In the fault injection attack, they will be using the don't care state during the transition. And in the Trojan attack, the foundry or the design house, people itself can include the some smallest amount of Trojan in place of the uh, don't care state. Thus, they can easily attack the entire FSM. And this will be taken care, will be spoken by Yashwant.
Thank you, Bhuvanesh. The systematic approach for AVFSM is considering having 4 steps. So first is to extract the state transition graph. Second is to identify the don't care states and its transitions. And third, to analyze the fault injection and to analyze the Trojan insertions. So this gives the overall idea of how the vulnerability factor of Trojan and fault injection is happening. So we'll go step by step. So first is to extract the STG, the state transition graph. For that, the input is being from the gate level netlist and the FSM synthesis report. It gives out the STG. So here, the algorithm consisting of 2 procedures, 2 steps. So the first step is to modify the netlist, and the second is to extract the STG. The first in the first step, this is the algorithm I'll be explaining with an example. So the every FSM will have a state FFs and non-state FFs, non-state FFs like counters. This the state flip-flops. The first step is to eliminate the non-state flip-flops by replacing with a net for Q and not gate for the QN. and then replace the state flip-flops with the nets for the Q and XOR gate for the D. The other input for the XOR gate is given from the input of the system. And all the outputs of the XOR gates has been odd and given to the output. It's called POOR. Then the QN are replaced with the NOT gates. So this gives the modified netlist generations. So this will be given to the STG extraction. In the STG extraction, you have a logical value for the thing what we got for earlier. Now we'll remove all the faults and we'll consider only stuck at one fault at the output OR gates. Since we are giving stuck at 1, the input for the OR gate should be at 0, 0. The outputs of the XOR gates will be 0 if only if both the inputs of the XOR gates are equal. So the ATPG tool will generate the input such that it will match the input state and inputs. So by this, we will have a state transition graph. So next comes the fault injection. How fault injection is happening? Consider the transition from 0, 0 to 1, 0. Here, the flip flops. Consider the S1 flip flop is having the setup violation. So if there is a setup violation in S1, the resultant will be in 0, 0. So there is the output, the resultant state is also 0, 0. So there is no impact on the security wise, but there is impact on the functionality wise. Consider the second example, transitioning from 10 to 01. Here, if I consider S1 to be setup violated, resultant in 11, which is not authorized to the system to enter into 11 state, but it's actually entering into 11 state. So here the fault has been injected. So for this, the algorithm has been developed to identify it. The output of this algorithm is the three sets: path violated, path okay, and path no effect. The example one which I gave is path no effect. So it doesn't matter what it goes. And the example two what I gave is path violated. Then we have two quantitative metrics to identify the easiness of attacking. So the susceptibility factor and vulnerability factor gives what? If both the values are high, it means it's very easy and it's very prone to attack. Then comes for the Trojan insertion. As Bones told, there are many don't care states which can enter into any of the states. If the don't care states is entering into the protected state, that makes the attacker easy. So this is a quantitative thing which gives the number of states it can enter into the protected states. So if this VFTRO is higher, then it's more easy to attack. Ideally, it should be 0. So the results will be continued from by Meghana.
So the proposed techniques are applied on the following benchmarks that are mentioned in the table. So the RTL state transition graph is compared with the extracted state transition graph that is obtained by following the previous procedures mentioned. So it is found that all the transitions that are in RTL STG are present in the extracted STG. So which means the proposed technique is quite accurate. And it is also scalable since it can be applied to a small multiplier to a complex processor as well. And the paper also does case studies for AES and RSA algorithms. So this for AES, it uses two encoding schemes. For the first scheme, the vulnerability factor is 0, which means that it is almost resilient to any of the attacks. But for the scheme 2, the susceptibility factor is about 0.15. So we can say that scheme 2 design is more prone to fault injection and Trojan insertion attacks. These are the encoding schemes that are used. The red ones denote the don't care states, and the black ones denote the states that are in the RTL design. Coming to the RSA algorithm, though the scheme 1 design has only one vulnerable transition, the susceptibility value is quite high, which is 0.66, compared to the scheme 2, which is three vulnerable transitions with SF value of 0.15. So I guess we can say from this that scheme 1 is more prone to the attacks than scheme 2 because of the higher SF value. So the paper also gives us a solution in order to mitigate the aforementioned attacks. Instead of using the scan flip-flops, programmable state flip-flops are used. They go into either reset or initial states whenever the protected state is being accessed by an unauthorized state. So depending on the select line, the multiplexer either chooses the next state value or the reset value and gives it to the present state. So it can be seen in the simulation result that whenever the attacker tries to access the protected state 000 from an unauthorized state which is 101, the present state will be the value of the reset state 001. So I guess finally we can say that the designer can use all of these techniques and compare various implementations of the same design and choose the best one with possibly no vulnerabilities. Even if vulnerabilities exist, the designer can still use the uh, proposed solution to mitigate it. So thank you. Let us know if you have any questions. Have a good day.
Yeah, thank you. Thank you all.